Sorry for the delay, friends.
Is it collecting audio?
It is now collecting audio, yes.
But is the manual sign is still like cancelled?
What's that?
That's good then. The little bars on the side.
Yep,
Yeah.
that's, there we go. All right. So, just real briefly on linear free energy relationships, and this is one, as I showed you last time, this is one thing you can do to interrogate reaction mechanisms by reference to other reactions, as we talked about. For these sigma para values, it's derived from benzoic acid deprotonation equilibrium constants. And it's thought that having something para gives you a sense for the resonance contributor, though we mentioned that it's imperfect because the negative charge on the benzoic acid is not directly conjugated to the ring or to the thing that's on the ring. Nevertheless, as you'd expect, electron donating groups make deprotonation less favorable because they destabilize the conjugate base. And then as you get to withdrawing groups, they make the conjugate base more stable. All right, you can do the same reaction but with meta-substituents. And you can see, as we talked about para-substituents donating or withdrawing, they can put either plus or negative charge directly adjacent to the ring, whereas meta-substituents can't. And so the impact of meta-substituents is a little bit smaller, at least for those that are resonance donors slash acceptors. So the amino group at the meta position doesn't change the equilibrium constant very much. Similarly, OH at the meta position actually makes the constant a little bit more favorable than hydrogen. Presumably, this is because at the meta position, the resonance donation matters less than the electronegativity of oxygen. And presumably the reason the oxygen substituents favor the deprotonation versus the amino substituent is related to the difference in electronegativity between oxygen and nitrogen. So there's sort of this trade-off between resonance donation and inductive withdrawal. And these are some, it's sort of nice that this lines up with some of your intuition derived from studying electrophilic aromatic substitution. Notice that inductive donors are also disfavor the deprotonation by similar amounts. Let's see, and then the withdrawing groups tend to be about the same or better at the meta position. And that's presumably because each of these nitro is a withdrawer via resonance, but it's also a withdrawer via an inductive effect. Okay, now suppose you wanted to know, you wanted to separate out possibly, as well as you could, resonance from inductive effect. You might choose a reference reaction which is phenol deprotonation. And these are the so-called sigma plus values. And the reason these report on resonance is because now the negatively charged group in the conjugate base is conjugated to the ring. In other words, if this is a withdrawing group, say a nitro group, I could move these electrons here, here, and then out onto the nitro group. And so you get a sense for I think I got this exactly backwards. Yeah, sorry, the arrows should be so stabilizing a negative charge here, stabilizing a positive charge here. Now, you might expect for this solvolysis reaction, things that stabilize positive charges should make it more favorable, not less favorable. So wouldn't the sigma values be backwards from what you would expect? And the answer is yes, and so to prevent that, we just add a negative sign. So for example, the amino group is a good electron donor and is directly conjugated to this positive charge, and therefore you'd expect this constant to be greater than that one. And we do take the log of that, but we put a minus sign in front of it just to make things consistent with benzoic acid deprotonation. You don't like it? It at least makes it so that you're on the same scale and it's interchangeable. All right, so once you sort of parse out the resonance effects from the electronegativity effects, that's where you see nitrogen is a really good donor, whereas the oxygens are less so because they're more electronegative. And then again with the resonance withdrawing effects, you see that the carbonyl is a great electron withdrawer, even better than trifluoromethyl, and nitro is really, really good. Okay, so we don't need to say too much more about that, but there are multiple scales, and you will, if you read the literature, I mean, this is a sort of physical organic chemistry thing. It's sort of like med chem for thermodynamics and kinetics. Let's do structure activity relationships. Let's vary the identity of some group and see what it does. So you'll see various people use different types of Hammett parameters, and you'll forget what they are, as I do, but now you know where to go back and see what they are. Okay. Anything else you want to talk about for linear free energy relationships? Okay, well, end chapter 8, and now let's talk about chapter 9, which is catalysis. We're going to deal with some pretty general principles. We won't really be talking about transition metal catalysts until we get to the transition metal chapter, which if I play my cards right, we won't, because I don't like those. Or rather, I don't know a lot about them, but maybe actually we should do it so we can all learn together. All right. Catalysis is about accelerating a reaction, and that is related to stabilizing the transition state. And an important principle of catalysis is that you have to bind or interact with, as a catalyst, you should bind or interact with the transition state more favorably than you bind the starting material, or what we sometimes call substrate, and more favorably than you bind the product. And let me show you why this is the case. So imagine a situation where we have substrate A and some catalyst, which we're going to call cat, and there is some equilibrium constant that describes binding of the catalyst to the substrate. And we're just going to call this the substrate catalyst complex. In other words, this is binding of the substrate by the catalyst before the reaction occurs. Then there's some equilibrium constant related to conversion of the substrate catalyst complex into a product catalyst complex. Meaning that the catalyst is binding the product, and then you have some equilibrium constant K3 that involves dissociation of the product catalyst complex to release product and to free up catalyst, and then you can go through a cycle again, right? And conceptually, this could be true for an enzyme, but it's also going to be true for lots of different catalysts. So let's imagine a situation where Situation one is where the catalyst binds the transition state better than A or B. So on this axis, you're going to have energy. And on this axis, you're going to have reaction progress or reaction coordinate, whatever you're using to measure the progress of the reaction. And let's imagine in blue is our uncatalyzed reaction. So there's our transition state and there's our product. Here you have A, here you have B, and here you have the transition state that's uncatalyzed. Now, let's deal with, in red, we'll do the catalyzed reaction. We go through some transition state to bind the catalyst to our substrate. Then we go through some transition state. Then we have some product catalyst complex, and then that breaks apart. All right. So in this case, the binding energy, how much the catalyst binds the starting material, is this difference here, right? And how much the catalyst binds the transition state, catalyst binding transition state, is there. Okay? Now, do you see that binding of substrate A by the catalyst moves that thing lower in energy? You go downhill in energy. And in terms of accelerating a reaction, that's in the wrong direction, right? Because you want to get over the transition state. So the thing that saves you is that this energy difference binding the transition state is way more favorable than binding the catalyst. And so overall, our activation energy, I'm going to draw overall our activation energy for the reaction that's catalyzed is here, whereas the reaction that's uncatalyzed, you've got this activation energy, which is much larger. Okay? Now, you can imagine a situation, and so this is a really important concept if you're designing catalysts. Sometimes your intuition tells you to do exactly the wrong thing. You think, oh, I want an enzyme, or I want to design a catalyst. I need to bind the substrate really tightly. Okay, if you do that, but don't bind the transition state, then what's going to happen? Let's say catalyst binds substrate A better than transition state. So same situation. Oops, I'll just copy, slide, and paste. Let's see, there we go. All right, so this time, let's suppose that we bind the starting material more tightly than we bind the transition state. This is our catalyst bound to our transition state. The activation energy for that reaction is actually greater than the activation here. So you no longer have a catalyst for the reaction. You have something that slows the reaction down. It's actually worse than the uncatalyzed reaction because you've lowered the starting material in energy, but you haven't done the same by the transition state. All right? Just qualitatively though, what if, would there be any problem you can foresee associated with binding the product too tightly? What's that? What would happen?
You don't get your product, you don't regenerate your catalyst.
Yeah, your product doesn't come off, you don't regenerate your catalyst. It's product inhibition, and we've talked about that before in kinetic equations. All right, so that's the really important thing. When you're designing catalysts, you have to have the transition state in mind. And that's why I think in a previous lecture we were talking about trying to evolve an antibody to catalyze a reaction that would proceed through a tetrahedral intermediate. Notice the molecule they used to evolve this antibody is not the starting material. It's something that resembles a tetrahedral intermediate that's negatively charged. So, right. Okay, so that's principle one, better bind the transition state. Principle two that you can use is the one that makes, I think, a huge amount of sense, and that is proximity-based catalysis. That is, if you can bring two things together, if you can bring the reactive groups together in the proper orientation, you can accelerate the reaction. So here is a particular substrate, and what I'm going to show you is mostly proof of principle, but it's related to something biological. And you'll see this, it's gotten much harder to publish proof of principle types of things in JAX these days, but it used to be that you just threw together a nice proof of principle and you had a JAX communication. So this substrate is meant to resemble an important biological molecule called acetylcholine, right? Only here the difference is that when you break this, when you hydrolyze this, eventually you're going to lose, when you hydrolyze this carbonate, you're going to lose CO2, and then you will liberate paranitrophenolate, which is which is colored, and you can watch this reaction happen via colorimetric assay. So there are enzymes that are called acetylcholine esterases. Acetylcholine is a neurotransmitter, and so you don't want that to persist too long and so you have this enzyme that degrades it rapidly. And the idea was, can we develop synthetic acetylcholine esterase? And so the approach was, I probably should just copy and paste this, but instead we'll draw it, even though I don't really want to. Okay, so the approach was to use a cyclic polyether that could bind cations. And the design principle here was, let's bind the positively charged tetraalkyl ammonium group. And so you're going to have lone pair electrons on the oxygen oriented towards the center of this cyclic structure. And man, I worry I'm going to get it wrong. Oh well. I think there were maybe 6 of these methoxy phenyl groups. This is why we like ChemDraw, because that way you don't have to beat yourself up while drawing. All right, so this, let's see. This portion of the molecule was designed to bind a cation. And then the question was, okay, that's going to allow you to grab onto the starting material via a non-covalent interaction. That's just ion dipole interactions, basically. But the question was, how do you catalyze hydrolysis of basically an ester or a carbonate? And for this, they were inspired by nature. There's a lot of proteases / esterases in which some nucleophile attacks an ester or an amide group, and you go through a tetrahedral intermediate, and there's actually, right where that negatively charged oxygen is, there are often functional groups that can hydrogen bond to that oxygen. This is the so-called oxyanion hole. It's like a pocket into which that negatively charged oxygen can pack and be stabilized by hydrogen bonding. And so the thought was, could they generate sort of a synthetic oxyanion hole by positioning hydrogen bond donating groups close to where the cation would be bound? And so they did this via a kind of complicated linkage, and they probably had to try multiple things to get the connectivity right. All right, then you have 6-membered ring containing nitrogen here. Oops. And basically they use this guanidinium functional group as the hydrogen bond donor. I'm not sure what they needed the stereocenters for, because they weren't actually trying to do anything enantioselectively selectively. But the idea is, okay, maybe if we bind the substrate, and we'll just use cheapo animation, maybe if we bind the substrate there, maybe that brings the carbonyl into such a position where it can be stabilized by hydrogen bonding with the guanidinium NHs. You'd have to, for that to be true, you'd have to imagine the ability of this arm to sort of swing around and get in position. And what people used to do in the early days of sort of small molecule catalysis design is they would actually use CPK models, build this whole thing, and see whether the geometry worked out. Anymore, you can build it in Gaussian, or you can build and minimize it and see whether you think it would actually bind the desired substrate. Okay, so and this is a proximity-based catalyst, but it's also an example of Lewis acid catalysis. And one of the most common examples of Lewis acid catalysis is hydrogen bonding. Remember, a Lewis acid is an electron acceptor. What's accepting the electrons? The Lewis acid is hydrogen bonding with the carbonyl oxygen that becomes negatively charged in the transition state. Okay, questions about that? So, Rachel, you're on a catalysis project, aren't you? Mm-hmm. Okay. Is this the heterobimetallic one?
Yeah.
Okay. So that's going to involve stuff that I don't understand. But how does Lewis acid play a role in some of that?
I think with some of our ligands, yeah.
Okay.
Mm-hmm.
All right. One other example of Lewis acid catalysis is the use of zinc as a Lewis acid, and this is zinc 2. In a lot of cases, you need something to chelate this so that it'll be soluble in organic solvent. 1, 2, 3, 4. That's a terrible. So you have the amino groups holding on to the zinc, and then you have some available axial positions where you can chelate water. And what the zinc does by binding the water is it lowers the pKa of the proton to such a point that it can be removed at physiological pH, and then you've got hydroxide that you can use for stuff. All right, so Lewis acid catalysis is another sort of very common way to do things. I guess we should talk about nucleophilic catalysis because that's a thing too. Any? Yeah.
Which was the pKa?
That would be the pKa for this proton.
Or just the proton?
Yeah. Now normally the pKa for water is like 16, right? So this is a dramatic lowering in the pKa, and that means you've got access to more hydroxide at physiological pH than you normally would. Okay, have you seen or heard of any examples of nucleophilic catalysis before? Lewis base catalysis. All right. One of the most common is in amide bond forming reactions or ester forming reactions. Suppose you have some leaving group X there, you have some nucleophile that ultimately you want to replace X with to do an acyl substitution reaction. You can accelerate that reaction using another nucleophile, and the choice of nucleophile is pretty creative. You use a nucleophile that's decently nucleophilic, but once it's on, it can't stay. So this is dimethyl aminopyridine, or DMAP, DMAP. And the idea is that before the nucleophile attacks, you have DMAP do the attacking, and that will generate a tetrahedral intermediate. Notice that because it's the pyridine group that does the attacking, you have a positive charge on the pyridine nitrogen. The leaving group leaves, and you end up with this intermediate, which is now even more reactive than the original leaving group was, because you've got a positive charge on that nitrogen. And there's no way, in contrast to regular amide bond formation, where there would be, or ester formation, where you could remove a proton to get rid of the positive charge. There's no such thing here. And so then the nucleophile attacks, you get a tetrahedral intermediate, and then you get your final product. And the idea is you're using a nucleophile. It's weird, isn't it? You're using a nucleophile to turn an electrophile into an even better electrophile. So you'll see that kind of thing a lot in acyl substitution reactions. Another example is use of use of a nucleophile to coax an electrophile into letting a leaving group leave to make sort of a super electrophile. So as an example here, here's sort of a binap type ligand for a phosphorus. Oops, that'll work. These bonds are sort of coming out at you. This is an axially chiral ligand that we don't need to worry about what its stereochemistry necessarily is. You have two nitrogens and they're both bonded to this phosphorus. Oops, phosphorus letter is not R. Man, what would we do in chemistry if we had used the letter R for an element? It would be kind of a pain, right? So this Lewis base can interact with tetrachlorosilane, or maybe that's not what it's called, I don't know, to cause one of the chloros to leave. And so you end up with a positively charged silicon with 3 chloros attached to it, and that's more electrophilic than just SiCl4 would have been to begin with. All right, so this is just a quick survey of lots of different catalytic reactions. What time are we looking at? 35 after? Okay. You weren't going to let me go till like 3:30 today, were you? Okay. Another popular area, and one that was awarded the Nobel Prize not long ago, is organocatalysis. And the idea behind organocatalysis is, can we do with small molecules the same kinds of things that enzymes do? So there are tons and tons of examples of this. I'm just going to show you a few. So as an example, let's take this aldehyde. Is that cinnamaldehyde? I think it might be. And you use as a catalyst the amino acid proline, which has a stereocenter adjacent to an amino group. And you do this to facilitate the aldol condensation of this aldehyde with itself. And again, why would you want to do this particular self-aldol reaction? I don't know. But in the early days, proof of principle was enough to sort of to be interesting. So what would happen is that you'd have the amino group of proline form an iminium ion with the aldehyde. Okay, I won't show you the mechanism of imine formation. Everybody okay with that? Once you get to the iminium ion, normally when you have an iminium ion with a primary amine, there's a proton you can remove here to get to the neutral imine. That's not the case with the secondary amine. And so then, because of that positive charge, this alpha proton becomes acidic enough for a weak base to remove it, and that generates an enamine, which is now neutral. Okay. Now remember, normally in the aldol reaction, you need to make an enolate. we've sort of made, and I'll draw, for example, an enolate or an enol. We've sort of made the equivalent of an enolate here in this enamine. Like the enolate, you've got lone pairs on a heteroatom adjacent to a pi bond. But we've avoided the negative charge while also installing something that's a pretty decent electron donor, this amino group. And so what happens next is that enamine acts as a nucleophile to attack another aldehyde, and you can push arrows however you want here, but showing the alpha carbon attacking the carbonyl carbon is good. And then there's multiple steps and hydrolysis of the enamine or iminium ion to get you that final product. So enamine-based catalysis is where you're using the secondary amine to convert your carbonyl compound into a better nucleophile. All right. There's also another type of catalysis that's based not on the enamine but on the iminium ion that can form. So imagine this alpha beta unsaturated carbonyl compound, and imagine that you want to do some kind of you want to do an addition reaction, 1,4 or conjugate addition at the beta carbon of this alpha beta unsaturated carbonyl compound. And imagine you want to do it in a stereoselective way. Carbonyl carbon, alpha carbon, beta carbon. Of course, if your nucleophile isn't chiral, good luck getting enantiomer enrichment there. But you can choose an iminium ion or rather you can choose a catalyst that is chiral, and you can take advantage of iminium chemistry. So, Rachel, is this the Macmillan catalyst? I'm not. You can't remember. That's okay. All right. I think it's an imidazolidanone. By the way, in organic chemistry, I'm not sure if I've said this before, imidazolidanone. It's considered cool to be able to rattle off the names of heterocycles like you really know what you're talking about, especially nitrogen-based heterocycles because their names are diverse. So, for example, a 5-membered ring containing nitrogen, unsaturated ring is called pyrrolidine, and a 5-membered ring containing 2 nitrogens with this arrangement, if it were aromatic, would be called imidazole, but if it's unsaturated, you can call it imidazoline. Imidazoladine. I don't know. Anyway, I clearly don't know this, but it's a pretty awesome thing to be able to bust out. So if you want to impress organic chemists, there's actually web pages you can go to. Let's look. Cube root of 24. Why on earth was I interested in that? Let's see. Let's search for heterocycle names. That looks fun. And this is only the beginning, because once you start bringing in degrees of unsaturation and places oxygens outside of the ring, it gets confusing. Pyrrole, imidazole, pyrazole, triazole, and there's multiple kinds of triazoles: piperidine, pyridine, pyrimidine, pyridazine. It gets a lot worse. Indole and so on. Anyway, if you want to impress people, I'm first going to ask you, why do you care what other people think? But once you convince me that it has to be that way and you do care, then there are lots of resources you can go to try to impress people. That's neither here nor there. So with this imidazolidinone catalyst with 2 stereocenters, you can make, similar with proline, you can make an iminium ion. I'm just going to copy this. And that, as we said, should activate you towards, that should activate this alpha beta unsaturated carbonyl compound. Notice that because of the alpha beta unsaturation, this alpha proton is held perpendicular to the pi system. There's no option to make the enamine here. And so you've basically done something like protonating the carbonyl oxygen, but you've done so in a controlled fashion because you now have a positive charge on the thing that's attached to the carbonyl carbon. You can draw a resonance structure where there'd be a positive charge on the beta carbon, and finally, the presence of these large groups can bias you towards attack from one face versus the other. So when the nucleophile attacks, it can come, you can get an antioselective nucleophilic attack. Then in the next step, you hydrolyze the enamine and you get the product. So organocatalysis is big, it's huge, and it's something to be aware of. All right, let's talk specific acid, specific base catalysis. And all right, we got 5 minutes, so tell me when I'm done. Have you heard these two different things, specific acid versus general acid catalysis? Never? Okay, good. You might hear it in biochemistry. You might not. It's kind of confusing, and it's confusing because it doesn't mean what you think it means. Specific acid catalysis, you hear that and you want to say, oh, I must need to use a specific acid, right? A specific one. Versus general acid, I must not care what the acid is. The acid doesn't matter. It's exactly backwards from that.
Why?
Okay, why? Because when somebody discovers something, they get to name it, and we don't all get to decide what the best way to talk about it is. So let me show you the real thing that matters for specific acid versus general acid catalysis. Specific acid catalysis happens before the rate determining step. So it's this situation where you've got this rapid prior equilibrium, which we dealt with early on in chapter 7. General acid catalysis is during the rate determining step. Okay? Now, let's talk a little bit more about specific acid catalysis. The specific acid, we're going to give the acid the name, the specific acid, and this equals, in water, H3O+, or it can equal the protonated form of solvent. Actually, the identity of the specific acid isn't important per se. What's important is that the acid-base step happens prior to the equilibrium. All right, so let's deal with some of the consequences of this. Let's imagine a situation where you've got group R, and it's going to be protonated by H3O+, and that protonation step is going to be fast to give you protonated form And this should start to look familiar because we talked about this a little bit when we were dealing with deriving rate laws. Then, in a subsequent step, RH plus, and there'll be some rate constant K, and it's a very slow step, will become product, that's protonated, and then we'll have a fast step after that that releases product and regenerates H3O plus. Okay, so we would say here that the rate of appearance of product should be K, rate constant, times RH plus. Now, we're not going to use a steady state approximation because this equilibrium is rapid and fast relative to this step. So as soon as we consume a little RH, we're going to generate more. And so we can use the expression for Ka for this equilibrium. Remember, Ka equals H3O plus times R over RH plus, right? That's the acid dissociation constant. So what that means is that we can rearrange that RH plus equals H3O plus times R divided by Ka. And then we can substitute that into our expression for the rate law, get little k times the concentration of starting material R times the concentration of H3O plus divided by Ka. All right, so if you were to do this under pseudo first order reaction conditions where you kept everything constant including the pH but you varied the concentration of R, all of this would be your observed rate constant. And that observed rate constant, you predict now, is dependent on pH. So if we were to look at this equation and increase the pH, that's going to lower the concentration of hydronium, and that should lower the value of the observed rate constant and slow it down. So if a hallmark of specific acid catalysis is pH dependence in the rate. However, it has been observed, and this is mind-blowing to me, even if you don't use the specific acid, you could use some acid HA, and suppose you increase the acid concentration while keeping pH constant. How would you do that? Well, you just put in the ratio HA to its conjugate base to keep pH constant. But we'll just show the concentration of HA. It turns out that if you control pH concentration, control pH, acid-base, increasing the concentration of acid doesn't actually change the reaction rate. So we'd expect the rate to be higher at pH 2 than at pH 6, but at any given pH, the rate is independent of acid concentration. And that is another hallmark of specific acid catalysis. It depends on the pH, but it doesn't depend on the concentration of the acid you use. All right. So when we get back next time, we'll talk about general acid catalysis, and you'll like that better because there are fewer steps to write when you do general acid catalysis. All right, happy Wednesday.